This meeting is being recorded.
Good day, Doctor. So this is the video presentation for the subject Bioinformatics 2, and my name is Yuling. My matrix number is A23CS0149. So for the mini project for this subject, my title is Leukemia Diagnosis System, and this is the user interface for my Streamlit application. So as we can see what we have in the homepage right now, we have the introduction to this application, what this application has. So we have data processing, EDA, model training, diagnosis, of which we can access from the sidebar here, and a little introduction into the leukemia types. So the topics of our discussion. So we have 4 major types. We have ALL, AML, CLL, and CML, which A stand for acute, C stand for chronic, L stand for lymphoblastic, A is for myeloid, M is for myeloid. So for features, the features of this application pretty much the description for what we have here in the sidebar, and then the dataset information. The source of this dataset is from the Gene Expression Omnibus (GEO), and then with the accession number GSD13164. And the features here, we have the gene expression and leukemia type. For this tool, let us look at the data loading so we can see it clearly. Let us load the data. So for features, this is the features we have here. The first 10 rows. So our total sample is 973, while we're only showing the top 10. So and this sample, when I read from the description, the dataset description from GEO, it said that the samples are obtained from leukemia patients who are just being diagnosed and they have not undergo any leukemia treatment yet, which is no chemotherapy or anything. So their gene expression are still unaffected by the treatment. And for the gene, we have 1020 genes in the column. For leukemia types, let us look at the labels. So the first column is the sample ID, which is going to link with the previous first column, and then the leukemia type. So we have 4 types, and I have assigned a numerical value to each type. So ALL will use 0, AML 1, CLL 2, and CML 3. So I will use this numerical value instead of the categorical label for the model training later. So next, let us look at the EDA. So the first bar graph we have here is the class distribution or the leukemia type distribution. So from our data set, we have 900 plus data, but our data set is not balanced, which means that each leukemia type has different sample size. As we can see, very obvious here, ALL has the biggest sample size. It has 436. AML, CLL has almost the same, which is 200 plus. With CML has the smallest sample size of 43 only. And then it's going to be smaller if later on if we split into 80-20. So we split 80 for training and 20 for testing. And the descriptive statistics across the genes, not so we are going to look at the statistic by leukemia types. So if we categorize them by type, and then we look at the mean value of each gene, is, as we can see here, is different for each type. And then this is the gene expression distribution in box plot and the correlation analysis. So we have 1,400 plus genes, and I cannot plot every single one in the correlation heat map because it's not so visualizable. We can do that, but we cannot then understand it because it's too much. So I have to pick the top 15 genes for the correlation heat map. And previously for programming for bioinformatics, I picked different genes for each leukemia type, which means ALL and AML, they have different gene here. As we can see, it's the same here, but then I did different genes for programming for bioinformatics because I figure I have to pick the top correlation for each type. But then we cannot then do comparison between these 4 types. So I figure I have to pick the top 15 genes overall and then plot a heat map so we can compare from type to type. So as we can see here, CL has less gene pairs with strong correlation, like only like 1, 2, 3, while ALL has a lot of gene pairs with strong correlation, but also it doesn't like necessarily mean it's good. Maybe it's going to cause like noise. So next, let us look at the model training. So I've previously actually trained the model because it's gonna take a while to run, and also because it's saved like as the cache. So I just have to click and it will show again. And there's a features here to clear the cache and to retrain. I've tried and it actually perform almost the same every time. So we just use what we have here in the cache. So I used three different models in the model training. So we have polynomial with degree 2, the rich regression, and then we have random forest and neural network. Previously in programming for bioinformatics, I have like 7 models, but some of them are not very useful. For example, simple linear regression and multiple linear regression are not very useful. So I figure I just have to pick the top models for this project. So I've picked the top 3, and then these are the metrics that we are going to compare to determine the best model. So we have the R square value here for train and test, and then the gap between these two, and the MSE value for train and test, and also the gap, and there's also a stability score. So for this stability score, because I was thinking, if we look at the visualization here, we can see that polynomial is performed well in, as we can see the value here, the test value is the highest, the train MST is the smallest. But if we look at the gap is bigger in MSE. Like in training it's almost perfect, but in testing it make like more error. And as in comparison with neural network, it made less error. Not like less, but in comparison with the training one, the gap is less. So I was thinking we have to take into account not just how well the model perform in testing, but also the gap between training and testing, like how well the data is going to perform, how well the model is going to perform when it encounter a data that they have never seen before. So I figured that I have to use the stability score. So this score is going to take into account both the test R square and also the gap between train and test. But still, the best model out of all 3 model is the polynomial with degree 2. And this is the individual model analysis. And it's plotted of predicted value against the actual value. And then next, let us look at the prediction and diagnosis. So we'll go through one by one. So first, let us look at the polynomial degree 2. So this is the overall accuracy. So it scored the highest with 97.44%. It correctly predicted 190 samples out of 192. This is for the testing, the 20% from out of 900 samples. So this is the confusion matrix. So we have the true label here, the actual leukemia type, and also the one predicted by our model. So we can see here, for example, CML, it correctly predicted 7, but wrongly predicted 2. It's actually CML, but it predicted CLL. Also, one interesting thing that I observed across all 3 models is that the models, it rarely, like they can differentiate between chronic and acute quite well. For example, CLL is never wrongly predicted as the ALL or AML, as we can see here, and AML or ALL is never wrongly predicted as CLL or CML. And then also we can see the detail of which sample does it actually wrongly predicted. So as we can see here, CML is wrongly predicted as CLL, ML, ALL. And then let us go to look at other model. So CML is actually CML is quite like poorly predicted across 3 models, given that small sample size, that is the model is not trained well with that small sample size, and when we put it into testing, it can wrongly predict the CML type. And we can also look at the wrongly predicted, and as what I wrote in my report when I put all the 3 tables side by side is that I can see for the sample at index 11, all 3 models has wrongly predicted this sample, and that they all wrongly predicted it to CLL. And also, I think 46 also, all 3 models wrongly predicted, and then they predicted to the same type. And we'll look at this one with 95.990%. And then also we can show here. And also this one is also the same. It never mass acute with chronic. So this is all for my Streamlit application. Should we look at the code? So we use quite a lot of libraries for this model development. So for this model training, and also to load that amount of data, and for visualization. So that's all for my presentation for the subject Bioinformatics 2 mini project. Thank you, Doctor.